Check it out now, y'all.
nanoHUB-U, online instruction.
Hello, welcome back to nanoHUB-U. Today we'll be looking at how to use more computational tools to compute behavior of multi-layer structures. And we'll specifically go over CAMFR. So if you remember from before, we were looking at kind of what are all the steps of CAMFR. And we said the first and foremost step was just to understand what sort of resonant modes we're looking at. So whether they're essentially guided, leaky, or radiation modes. And we said that guided and leaky modes tend to have a certain well-defined resonant frequency and are strongly localized and have certain factors associated with them. Whereas the radiation modes kind of travel freely and don't necessarily have any specific frequency that they're strongly associated with, but of course can occur at every frequency. And of course, we left it off at that point and we hadn't shown like the rest of the steps to get to like kind of a useful solution. So as the next step, we're going to look at Lorentz Reciprocity. And so what Lorentz Reciprocity does is it basically kind of uses Maxwell's equations to evaluate what happens at boundaries between different media. Okay, so this is just an example of like kind of a structure that you might want to look at, the reciprocity relationships. And so the idea is to start off with Maxwell's equations and to write down two different sets of fields, E1 and E2, which are present in two different media. And then the idea is to actually like combine what's happening like between the E and H fields, and then to basically compose a pointing vector in S, and then to take the divergence of that pointing vector and to say, based on the conservation of energy, that difference of pointing vector should be equal to difference of power dissipated within that volume, like at that boundary. And so then if you integrate that over the volume and then use Gauss's theorems, then that shows that you get a surface integral which has to be equal to volume integral for those two quantities, basically the pointing vector and the volume integral of the dissipation. And so then you can actually then rewrite that a little bit by taking the derivative with respect to z of those two pointing vectors, and then take the dot product with respect to like a unit vector in that normal direction z. And then that has to be equal to the difference of the power dissipated. And so now basically that's giving us kind of a symmetric relationship between the E and H fields and also the currents that will be occurring like right on those boundaries. And so the reason why it's so useful for us, though, is that in particular what it's going to tell us is that if you have two media, like, you know, the starting and ending media, and then they're both Z invariant, then that means that this difference of the powers dissipated has to be equal to a constant. And so then, since we're taking the derivative with respect to Z, then that means that you integrate that out, the Z dependence, and then the Z dependence derivative must be equal to 0, right, by definition. And so then you get that the pointing vector, this E cross H dotted into the normal direction, integrated over the surface must be equal to 0. And so probably the easiest way to think about that is just that, like right at that boundary, the total input power must be equal to total output power. So hopefully that makes sense. So in other words, we're not creating or destroying energy right at that boundary in the case of like Z invariant media. And so this is like discussed in more depth in Peter Beensman's PhD thesis from the University of Ghent in Belgium, which was entitled Rigorous and Efficient Modeling of Wavelength Scale Photonic Components. So continuing on, so if we basically are able to write down, based on this Lorentz Reciprocity relationship, what the E fields look like. And so like we said, there's the incident field, and then there's all the reflected fields, like with different wave vectors in the perpendicular direction, as well as like all the transmitted modes. Then we can define overlap between like pairs of modes based on like the E fields in the mth mode, and then the H fields in the nth mode. And then that can actually allow us to obtain the transmission coefficient based on that overlap coefficient. So in general, we get to write down, just by taking kind of like the product with respect to like these HIs and HJs, like effectively like that the transmission coefficient will be a sum of like the overlaps between EI and HJ, and then EJ and HI. And then that would be equal to the overlap of the Pth coefficient. And then we also have this reflection coefficient here. And then this reflection coefficient is computed in very similar fashion from all these overlap integrals. Has kind of the difference of these E and H fields. And so, of course, if you add both the transmission and the reflection terms together now, of course, this has to be adding up to like the overall incident power, which is the Lorentz reciprocity condition for Z invariant media. So once we have the formulation set up like that, now we can effectively use the standard S matrix scheme. And so this is essentially the same thing that we showed earlier for like what the composed P plus 1th matrix element will be in terms of the Pth matrix element for the S matrix. Okay, so in this case, we're basically assuming that we already know these Rp plus 1 and Tp1 terms, right? So these are kind of our assumed S matrix, and then we're calculating this Tp plus 1, Rp plus 1, etc. Okay, and then the indices just indicate like which direction we're going, whether we're going from P1 to P plus 1 or vice versa. Okay, and so then, like we said before, we're kind of forced to basically embed all the physics of the interaction in these like S matrix layer interfaces. So these Rp, P plus 1, and then the Tp, P plus 1 terms, which are combined together in kind of the fashion presented here. And so this basically ends up also, like as you can see, taking the inverse of 1 minus this reflection coefficient at that new interface times the overall reflection coefficient you had before. And we know that both of those terms should be less than 1, so that means that the overall 1 minus products of R should be less than 1 as well. And so then we take the inverse, so that could in general be slightly greater than 1, but we're also constrained by the transmission, which is less than 1. So overall it shouldn't grow above 1 at the end of the day. And then it depends on, of course, that relationship between the P plus 1 and the P plus 1. We know in general that the sum of those squares should be equal to 1, right? So that's why you don't end up with an unphysical transmission or reflection. And so then we just keep composing that, starting from kind of the identity matrix as our first guess, until we've included all P plus 1 layers of the structure. Okay, so it's very similar to before in that sense. And now, if we actually have a periodic array of layers in the Z direction, now keep in mind that we know that it would solve this eigenvalue problem where we basically would have the eigenvalue equal to kind of a complex exponential, like e to the minus j beta p, where p is essentially the periodicity of the structure. And so if we have something in that form, then we can actually use what's called singular value decomposition to kind of calculate what this A matrix will be made out of. And so then this actually allows us to much more easily take the inverse of our matrix in order to kind of properly calculate the eigenvalues and eigenvectors that we care about. And so you can see here, this is kind of a standard numerical technique where we take our A matrix, which was from above, and then we would break it up into three terms, the U and VH and the sigma. And then the sigma basically represents the eigenvalues of the problem of A, and then the U and VH are unitary matrices that kind of help us construct the eigenvectors later on. But then the other nice thing about them is that when you try to invert the A matrix, then it's actually much easier once you have a singular value decomposition, because V transpose can be easily inverted to give us V, and then of course that'll move to the front, and so then we get V times the diagonal of essentially like 1 over all the eigenvalues, like from sigma, times the inverse of U, which we can write as UH. Okay, so what does that end up looking like? So in particular, what's nice about this system now is that you can use this not only to calculate transmission through a finite number of layers, but actually infinite number of layers in, say, a 2D perfectly periodic photonic crystal. And so now what you do is you take, say, a square array of rods in air, and then you basically represent that as a system in which you have like only basically two layers, right? So you have one layer in which there's a dielectric present, and then one that's pretty uniform. And then you basically break it up into this layer, and then this layer, and then you create like a wall to create that periodic symmetry, or like a reflection symmetry in the problem. And then you also have this periodic behavior in the C direction. And so then that can be calculated using the singular value decomposition. You can take the inverse, you can get essentially like what the wave vector of the problem should be. And then that allows you to solve the essentially perfectly periodic and infinite structure using this layer-based approach, using only two layers, right? So it's actually a very small problem computationally, but it can give you very nice results, as you can see here. If you compare this with what we had earlier, you see again, like basically compared to week 1, we have like this frequency versus wave vector, and then you effectively have like a very rapid rise in the frequency as a function of wave vector, and then you have like this finite splitting, which is caused by the presence of a large refractive index contrast between the green regions and the white regions, which are portrayed there. And that happens particularly at the boundary of the first Brillouin zone, which is represented as the X point. And this result is closely similar to the MIT photonic bands result that was shown in week 1, but computed through kind of a different method in which you don't necessarily directly solve the so-called master equation like done before, but you actually are just solving the problem of what happens to the S matrix using a singular value decomposition and taking the limit that it repeats infinite number of times. And so, of course, that can be extended to more complex problems as well, not surprisingly. So if you have a structure in which you have two triangular lattice photonic crystals that are separated by a small air gap, then that's kind of a row of defects or a waveguide. And so you have a 2D photonic waveguide in this case. And you can kind of split this up so that you only have to represent effectively like one period in this direction, in this E direction. And you can kind of create a slice in this direction in order to look at how strongly is the light going to be confined. And so not surprisingly, if you're well within the band gap, it is strongly confined. So most of the fields are localized within the low index air region. And then you also get, instead of the band structure we had earlier, you not only have a band gap, but you have like this waveguided mode, which kind of lives within the air, but only in the air. And this, in this case, is an even mode. Of course, in general, there could be even and odd modes with respect to the symmetry of the system. Now, this is just showing very briefly, like kind of what is the overall computational structure of CAMFR, in particular showing that it kind of breaks up its representation into two parts. One part which is basically focused on the abstract representation of scattering matrices and to basically represent different problems, like different types of solution methods, using like different the sources. Like, of course, there's the band structure mode that we were looking at. And then there's also kind of like this waveguide mode that was the last slide, as well as like a source for cavity. But then there's also like a number of like things that are, you see here portrayed on the bottom, that are kind of more geometry specific, that may include dispersion relations and mode profiles, overlap regions, etc. Okay, so you kind of have that sharp distinction. And then the idea is like, if you can make these scattering matrix problems very abstract, then it's much more reusable than it would be otherwise. And so now I'm going to go through like what is like some of the code that you could write in order to solve problems in CAMFR. And so CAMFR is based on Python. So it's a Python library. So once you're able to get it installed, then you would effectively like set a wavelength for the structure. Here it's just taken to be 1. That's kind of arbitrary units. And then you allow up to 20 different modes. So set n of 20. And then you can choose the polarization that you care about, choose the materials that you want to include, and then you can stack them on top of one another using the so-called slab command. And so then this slab command will basically stack 2 units of air. So if we take like kind of the unit length is 1 micron, then this would be 2 microns, then half a micron of gallium arsenide, and then another 2 microns of air. And then you use slab calc and slab plot to both calculate and then plot your results. So here's like what you get. So, I mean, not surprisingly, you're going to get index guided mode in gallium arsenide. And then this is just showing like kind of how the spatial position, the E field, kind of matches up with that original stack design that we showed earlier. And so you see that's heavily localized to the gallium arsenide mode with just exponential tails just outside. And then you can also plot like these eigenmodes that you're getting. And so you can see that these are almost exclusively like waveguided modes in the system as opposed to radiation modes. Okay. And now you can, of course, do more complicated problems. I mean, that would be the main justification of doing this. In 2D, for example, you can assume that the gallium arsenide only has a finite length. So it's like a very short index-guided waveguide. And then you can look at both the transmission and reflection across this gallium arsenide structure. Okay, and so basically you have your source here on the left, transmission in this direction, and then basically reflection R12 over here. So you construct this in a way that's kind of similar to before, but you have like basically a stack of the wave-guided slab and then air, one on top of the other. And then you calculate what's happening with that whole 2D stack. And then you can output for example, the reflection. That's what I'm outputting in this code. And then what you can see here is that the reflection is going to increase as you increase the length of this waveguide, which kind of makes sense because if it gets sufficiently long, then you can have like a resonant reflection effect. Whereas before, if it's very short, almost everything is going to just pass right through. And so that's kind of like happening at like very short distances. Of course, if you made it long enough, then of course it's going to go back down again. So there will be Fabry-Perot type oscillations. Something else that's nice is you can do 3D problems if you use cylindrical symmetry. And so then this is just an example where you might have like basically a piece of gallium arsenide that has like this sort of structure surrounded by air and then absorbing boundary conditions on the top and bottom. And then it can be represented as a cylinder from the top. Okay, and so then this is actually a very nice way to model like vertical cavity surface emitting lasers if you can represent things as 3D circles. Now, if you look at what's happening in terms of the reflection of the cylindrical stack, it kind of makes sense that like as you increase the radius, then you start to see like certain resonant peaks at this fixed wavelength that we're concerned with. So you see like a peak here at a radius of 0.12 and then another one around like 0.29. And so there are a number of resonances that can be picked up. You can even do stuff like split incoming light into multiple pathways using this code. I don't have time to go through it in detail, but you can see effectively that if the light's coming in from here, you could potentially have a 50-50 splitter in both directions, or maybe like a low loss but non-zero loss. Of course, you have to have at least 3 dB loss essentially in each branch because of energy conservation. But what's nice about it is it happens in very short distance, like on the order of a wavelength or less, which compares very favorably with much larger index-guided waveguides. And then finally, I wanted to briefly go through a more detailed example with a vertical cavity surface emitting laser in which you basically would not only have like a cylindrical stack of one material, like gallium arsenide, but you would have a whole bunch of distributed Bragg reflectors on the top and bottom, which would help kind of create like a higher quality factor mode on the top and bottom. And then this is just showing like what kind of mode you can get. Like this is of course like a cross section, and then this is the basically the radial direction, and then the azimuthal direction kind of comes out of the page here. And then this is the Z direction, so you can see it's strongly confined within both Z as well as like within the radius by kind of a combination of index guiding and photonic crystal band gap type effects. And so then this is very good for generating like a high quality factor laser mode. And so then this is just showing like how does the wavelength depend on both the diameter and as well as the threshold gain. Okay, so that pretty much wraps it up for transfer matrix methods. And so next week, we're going to look more at finite difference time domain methods as kind of a complementary alternative to what we already discussed. And I would recommend, in order to get started on this, you might want to look at the MEEP tutorial, which is on j2j.mit.edu/wiki. Thank you.